Okay, so welcome back to another video. Here's a improper integral from over the positive reals, and everything inside our integrand is kind of a little bit of everything, you could say. So we have the natural log of 1 plus x divided by 2x, all divided by the square root of x times 1 plus x, and then multiply by the natural log of x. This one's going to be quite interesting to work with, and it's not going to be that long to, calculate, but also there's just a lot of things going on that we need to do. Some of it, of course, being involved that we need to do a little bit of some u-substitution. There's actually going to be some hyperbolic functions involved, specifically that not really a substitution, but more of identities that we will be substituting to, whatever of the equating of the integral that we're trying to simplify. And with that, basically also that including is that there's going to be a lot of things we're going to change in terms of algebra manipulation, etc., etc. And then eventually it will just lead to just calculating the simple in the form of a trigonometric integral. So just something as simple as that. Well, the antiderivative rather is a trigonometric function. So with that out of the way and everything, let's just actually jump right in. Let's do a nice little u sub over here, where I'm actually just going to call this x. We'll let x equals e to the power u. Then dx is then just e to the u, then du. So substitute this all back. So I'm just going to call this whole thing capital I. So then our integral then, if we plug, infinity, that's x. So that means u is going to be infinity. And if I have x equals 0, then that means u is going to be negative infinity. Then put this back. So I have the natural log of, 1 plus e to the u, and then divided by 2 times e to the u. All this being divided by, so that means e to the u over here. So I'll actually write this in terms of the exponent. So it's going to be e to the power u divided by 2, then multiply with 1 plus e to the u, and then ln of e to the u. So that's just going to be u, and then multiply with the dx differential. So e to the u and then du. Okay, so here's what we're going to do now. So there's actually some manipulations we're actually just going to change over here. So what we're going to do is that, so negative and then positive over here. So inside of our natural integral, our natural log function on the top, what I'm actually going to do is I'm going to multiply e to the negative u and to both the numerator and the denominator. So with that being the case, that's going to change things to e to the negative u, and then add this with 1. And then multiply with, or divided by 2. And then this is still going to be e to the u just from outside, okay? And then next thing, what I'm going to do here is I'm actually going to multiply our denominator from what we're looking at is going to be everything multiplied 2 times e to the u divided by 2 to both the top and the bottom. And so what that will do is that that's actually going to change to 2 times e to the u divided by 2. And then multiply with e to the power u divided by 2. So then that's just going to change some things up inside of our 1 plus e to the u when we actually multiply that out, or rather divide in this case. What that will yield is that this is actually going to get, what will give us is that it's going to be e to the power u divided by 2 plus e to the negative u divided by 2, all this being divided by 2, and then and then that's still multiplied by u and then du. Okay? So then we can actually use the nice identity. So let me actually switch to a different marker for this one. So we can use the nice identity so that the hyperbolic cosine of u is equal to e to the x plus e to the negative x and then divided by 2. It's also equal to e to the 2x plus 1 and then divided by 2 times e to the x. So why I write 2 different identities, they'll be important later. So just keep that in mind. So what you'll notice is that that can actually be substituted back for over here. So then now we're going to be left with, and just factor out the 2 outside of that for 1. And so that's just going to be 1/2 and then multiply the integral from negative infinity to positive infinity. And then now we just have the natural log of, so I'm actually going to factor out the e to the minus u divided by 2 from the inside. So e, then negative u divided by 2. Then over here, this is going to be e to the negative u divided by 2. Add this with e to the positive u divided by 2 and then divided by 2 over here. Okay. And then we're going to see that, so e to the u and then e to the u, that's going to be, or divided by 2. So you multiply that together. So you just get e to the u, and then that e to the u will cancel. Then we'll just use this for the definition of the hyperbolic cosine. So then that will just become u times hyperbolic cosine of u divided by 2 and then du. Okay. And now next thing we'll do here is that, of course, applying the natural law properties. So I have 1/2 then the integral from positive infinity or negative infinity to positive infinity. So apply the natural logs over here. So then this will become negative u divided by 2, and then add this with the natural log of the hyperbolic cosine of u divided by 2. So that same substitution over here. So close that off, and then divide it by, so this is still going to be u, and then hyperbolic cosine of u divided by 2, and then du. Okay, so now we're actually going to split this into a sum of integrals. So now just factor, or not factor, but multiply the 1/2 into each of the functions respectively. So then first thing I'll get is that this could be 1 divided by 4, then of course constant, so that's why I factor it outside. So negative infinity to positive infinity, so du, and then divided by hyperbolic cosine of u divided by 2, so because those u's cancel out. And then next is going to be at this with 1/2, and then the integral negative infinity, positive infinity of the natural log of the hyperbolic cosine of u divided by 2, then multiply or divided by u times hyperbolic cosine of u divided by 2, and then du. Okay, so here's something interesting over here. So if you take a look at this function over here, you're going to notice is that if you inspect the function itself, that's actually an odd function. You can actually test this just to plug negative x, or negative u in this case, and see if you get the negative of the same function over here. That's what it is. And if you actually were to take the integral over the same, positive or negative L from between the equidistant length, if you take that integral of an odd function, this is actually just simply just going to disappear, and that this is just going to equal 0. So that actually just leaves that out of the way, eliminates that, and now we just have this integral. We need to solve the hyperbolic cosecant. And now the next thing I'll do is that we utilize that definition of the hyperbolic cosine of u, which 2 to the e, the far right equation, 2 to the power x plus 1, and then divided by 2e to the x. So we just substitute this back here for that definition, and that will reduce down to just negative 1/2, then multiply by the integral negative infinity, positive infinity of e to the power u divided by 2, and then divided by e to the u, and then plus 1 du. Continuing forward, so negative 1/2, and then integral infinity, negative infinity. So this will be just e to the u divided by 2. I'm going to write the e to the u as the following. So plus e to the u divided by 2, then square, and then du. And then now you can actually now apply a nice little u sub. We'll call this t. T equals e to the power u divided by 2. So then dt is then just equal to 1/2 e to the u divided by 2, and then du. And as you'll notice that you're going to have some stuff that cancel out. You can actually move that 1/2 back in, and then that'll just disappear by itself. Therefore, that's just simply just going to be the negative integral of infinity, and then we'll plug in the new bounds. So then this will become 0 to positive infinity of dt divided by 1 plus t squared, which therefore that's just going to be negative arctan of t. Evaluate this from infinity to 0, and as you notice that you plug in the bounds, your final answer indeed is just simply just going to be negative pi divided by 2. For that is our final answer to everything of the integral we were given. That's, seems like a lot that's we're dealing with. So what is it, 1, 2, 3, 4 different kinds of functions? Well, the natural log, so 3 different types, I should put it that case. And we just added some new functions that we just saw, hyperbolic cosine, then we just ended up with a hyperbole, or a trigonometric antiderivative that we just solved, where the antiderivative is a trigonometric function. Plug that in, and then we actually get the answer that, simple. So yeah, that's pretty cool if you ask me.